Great. It's good to be here. My name's Ken Levinson, and I'm the executive director of the Passive House Network. And we'll be talking for the next hour about Passive House and hopefully giving you a well-grounded introduction. Feel free to ask questions as we go through it. There's a fair amount of material to move through, but we'll try to be expeditious. Um, and yeah, feel free to put questions in the chat. I have the chat open, and and if I don't see it or you don't get to ask the question, there should be time at the end for us to discuss. So let's get started. So just first, the Pass House Network that I'm the executive director of is a nonprofit. We are nationally focused from coast to coast. Um, we are part of a international passive house association, and it's really one of the wonderful things about it is the global nature of it and working with folks from around the world. We have chapters across the United States, including Passive House California, which is a very active chapter, and encourage you all to find out more about that too. And I'll drop some links in, but certainly on our website, passivehousenetwork.org, everything is pretty easy to find. We're, as an organization, focused on education, on training, on capacity building, on connecting people. Really, it's peer-to-peer knowledge sharing that is the superpower. Passive House people are very open and giving of what they're doing with their work because they want to see everybody else succeed. It's a really kind of a fun dynamic because a lot of folks are coming to it from a sense of mission, a sense of wanting to make a better, more sustainable environment and better outcomes for everybody. So really, if everybody doesn't succeed, then nobody succeeds. So it reinforces that. The cornerstone activities that we have, oh, let me put on the proper pointer. Here we go. Is the Certified Pass House Designer, which is geared for architects. We have a hybrid version of that live online on demand that's very accessible, affordable. There's an amazing incentive from PG&E that you should try to take advantage of. And I'll mention at the end the schedule, and the next one is kicking off April 9th. We also, we work with another group, eMove Passive out of Colorado that provides the tradesperson course, and we work with the Passive House Institute, building certifiers and organizations around the world. Just a moment about me. In my background, I'm an architect, trained and practiced for a couple of decades. I'm based in Brooklyn, New York, on the other side of the country. And it was a real wake-up call to me in a way when I had the chance to have my first project back in 2010. And I believe that was about the time that W. Tahan was doing the first Passive House project in California, in Berkeley. Um, and For this project, I came at it with climate passion and wanted to, I was very excited about the crushing the heating demand and the energy efficiency and the performance of Passive House. My clients, on the other hand, weren't necessarily jazzed by that. They were coming at it, with consumers, thinking about their family, thinking about the investment. And I really had to change my talk a little bit and not go with my passion, but speak to theirs. And it was about thermal comfort. It was about quietness the Passive House could provide, uh, the city kind of going away into the background, the resilience and the quality of the construction, the indoor air quality uh, for the health of their family. So all of these things were really important. And the fact that it was energy efficient and could save them some money and pay for itself down the road kind of made it much easier. And so from that, it pretty quickly had a growing sense of that while energy efficiency is maybe the headliner with Passive House, it's the fact that energy efficiency really underlines and helps drive really fundamental values and wants of people. So for the occupants to have that comfort, as this family did with indoor air quality, fewer allergies, quiet, affordable operation, and high levels of satisfaction. And you could see how these things kind of then flow through to owners and uh, and have happier occupancy, lower vacancy, a more durable asset, really what becomes a lower risk investment. So there are a number of ways we could go into that more and more, but let's leave that there for the moment. The logic of Passive House is interesting, where it came from. Passive House is building science. It's not some crazy esoteric thing. It's all the basic physics that folks have been dealing with for a long time. It's just kind of really focusing it and giving it the attention, the important things, the attention that they deserve. What am I talking about? Well, an interesting part of the origin story of Passive House was that the German physicist who really started the modern Passive House movement, Wolfgang Feist in Germany, has this quote. He says, "I was working as a physicist. I read that the construction industry had experimented with adding insulation to new buildings and that energy consumption had failed to reduce. This offended me. It was counter to the basic laws of physics. I knew that they must be doing something wrong. So I made it my mission to find out what and to establish what was needed to do it right." So here you see this German scientist seeing the building industry applying insulation, but not having any beneficial result from it. And we could see that today. And the contractors, why do we need to do this? The owner would be like, why did I do that? It's not unlike cooking, where you have a few key aspects, elements of cooking. Wonderful book, Salt, Fat, Acid, Heat, you may be familiar with. And if we master these basic elements of cooking, we can make a great meal. It's similar with what drives performance. And Passive House kind of uniquely, again, forces us to focus on that. Another aspect that we'll look at here is in teasing this out is the just the basic kind of conceptual definition of what a passive house is. What is the performance level? And it's a conceptual, I would say a platonic definition. Most buildings don't actually operate this way, but it is formulates the the kind of conceptual structure of it. So this is a little wordy, I apologize, but I think it will help ground it. A passive house is a building for which thermal comfort can be achieved solely by post-heating or post-cooling of the fresh air mass, which is required to achieve sufficient indoor air quality conditions without the need for additional recirculation of air. So what's really interesting about this is that it starts with thermal comfort. It's about the occupant. It's about the occupant being comfortable. It's not about just hitting an energy efficient number. Um, it's about a state. And we're achieving that thermal comfort by heating or cooling, post-heating or cooling, the fresh air mass. So the ventilation air that's coming in, fresh air, not recirculated air. And we're only bringing in enough fresh air mass to achieve sufficient indoor air quality conditions. So we want to make sure we establish good indoor air quality, but we're not going to overventilate, because if we overventilate, we're going to lose energy. And then it's going to be harder to post heat and post cool as well. There's a balance there that we're striking, um, uh, since we're not recirculating. And uh, so because we're not recirculating and these other conditions to achieve thermal comfort through this low ventilation volume, relatively low, you need a very good thermal enclosure is the bottom line. The kind of image we have is if in the wintertime and it's freezing cold outside and the power goes out, just a handful of candles could keep you warm and and if not completely comfortable, quite comfortable enough. Um, with a light sweater on, normal conditions. Um, and so what Passive House is doing with this definition and approach is kind of inverting our normal sense of things, where efficiency is typically seen as a sacrifice. Um, Here, efficiency is actually driving greater comfort and health. And as we're pushing for greater comfort and health, we are gaining energy efficiency. So it becomes a virtuous reinforcing cycle. So you can sit by a window on a cold winter day and be comfortable without any radiators about. To achieve this thermos that's going to allow us to maintain comfort and high quality indoor air quality conditions, we're focusing on five principal aspects of the building physics. Now, there are other things, there's orientation, there's massing, uh, a realm of things, but in terms of the structure itself, the architecture, we're looking at climate specific levels of insulation, number one. Number two, that insulation needs to be truly continuous, that we are eliminating thermal bridges, and we'll come back to that. We'll discuss all this a bit more. Along with the uh, insulation continuity, we want air tightness. We want airtight continuity. We want control of that indoor air. We want to keep the pollution out. And then we want high performance windows and doors with solar protection. The windows and doors are going to be continuations of the heating, of the insulation and the air tightness. Uh, they will provide some solar gains, but these are not passive solar houses in the historic sense. We are not needing to overheat with the solar gains. We want to keep it quite modest and quite balanced. Um, and so the energy model is very important in that. With that, we can open the windows, and natural ventilation is an important part of passive house strategy, but we can't depend on it. We're also want to have solar protection. We want to minimize overheating in the summer and minimize the demand for air conditioning um, as well. So glazing is very carefully considered in passive house buildings. We're not just wrapping buildings in glass and going kind of willy-nilly. Because we can't rely on natural ventilation, although when we can have it, great. We want to make sure we have a very good ventilation system. And so that ventilation system is going to be distributing air throughout the building, and we're going to have high efficiency heat recovery, right? So we want to make sure we're keeping the building temperature steady and the outdoor temperature as it is. We're not losing the heat or the cooling through the ventilation, or at least not very much. These five aspects, which we really drill down on, are all put into the energy model, which is the Passive House planning package. It's an Excel spreadsheet. It's very kind of user friendly in that it's instantaneous results. It's a simplified model based on dynamic modeling, based on data, and simplified, given that it's a low energy building that doesn't readily react to the environment. And what we can see is typically up to a 90% reduction in heating demand, and overall energy reduction on the magnitude of 60, 70 or so percent. So significant, much easier to get to net zero. Um, we'll see some of the different building types. We have multifamily housing here. It could be from the luxury end of the market, also the affordable end of the market. Um, we see affordable housing as a huge part of passive house growth, and was initially one of the main drivers, affordable housing, social housing in Europe, of passive house. So really great because we're bringing high quality construction to folks that may have not been in great construction to begin with, or in more polluted areas. So uh, it's good for a number of different reasons. They can be different types. The architecture is not so strict. You pretty much, you know, you could you like I'd like to say you could do anything and make it a passive house, but you really can't do anything because that's a little extreme. But you have a lot of flexibility. The rule is really you can do things to make it easier to hit the standards or do things to make it harder. And part of that optimization process with your design is that balance. And the more you can incorporate passive house strategies that make it easier to have a high performance building from an energy standpoint, um, it's going to be much more straightforward in terms of delivering. But here we see an office tower in Boston, a big university building in Australia. Part of the passive house has become, and it's an important part, is aligning with our all electric, all renewable energy future. Typical way we're looking at energy use with buildings, EUI, source EUI coming from the coal power plants, the natural gas power plants, um, those energy losses along the way to a building, and and ultimately the use. And this is really based on a carbon emissions approach, which totally makes sense historically. But as we move to an all electric power supply that's fueled by all renewables, um, what really comes into play and what's most important is the simultaneity of the use with the generation, because the different renewables based on location and climate and characteristics of the grids, uh, you're going to have a different mix of renewable supply. And depending on how you use that energy, it's either going to line up directly with that supply, or you may need some short-term storage day to day, get you through the night, or long-term seasonal storage. And so it's rating how you're using the power uh, to a hypothetical, hopefully not hypothetical, the future energy distribution reality. Um, so what we are trying to do ultimately is tune the building to the grid. So it's not only efficient in terms of the building, but it's efficient in terms of the build out of the grid. Because what we have in typical kind of net zero family homes, as an example, even if they're more energy efficient than what we would typically be doing, there's still going to be a significant seasonal gap in the winter time, huge gap between where our renewable production is typically lowest and then where in the summertime we don't need as much, but we've got all this power. So this is a net zero single family house um, that really isn't net zero, right? Because it's not producing the energy when they need it. So there are additional losses. So for this to be truly net zero, it would need to actually produce even more energy to make up for those storage losses that would need to be provided to move this power from the summer to the winter when it's needed. In Passive House, we're crushing that heating demand, we're reducing the overall electric load, and we're tuning the building. So we have a much smaller gap in the wintertime, and we can dial down that renewable production. So the solar panels can really be cut substantially and still hit quote unquote net zero. We really move away from the net zero metric, but that's a whole other presentation. It's really about efficiency of resources rather than offsetting one with the other, because with the offsets, it's really not that efficient. One quick example of what moving to Passive House and why we want to do it. Massachusetts has just brought on mandating Passive House in a number of ways, calling it the thermal code for their commercial buildings, but literally Passive House for multifamily. And what they did is a study excuse me, where they showed a school and the load on the electric grid due to heating and cooling of the school. And for the model code where they had gas heating, you had a summer peak of the electrical, and there's no electric to speak of in the winter because the heating is with gas, not electric. Now, if they just move to electric heating with the model code, their peak on the grid is going to be over 4 times their summer peak. And so all of a sudden they're blowing up the grid capacity with this move. And so this is one of the big pushes and problems that are stressing the grids, is this capacity shift. But if they build the school to passive house levels, the heating demand is no greater than the cooling demand. And so there is no new peak. It's the same old peak. Uh, and so there's no need in terms of this building to increase the capacity of the grid. And so an investment in Passive House could really be seen as an investment in the grid and why they see these buildings as being grid friendly and have pushed for investing in them. Just a quick note, more local, a retrofit here in Sunnyvale, California. Um, 1,500 modest home went for net zero with a 9 kilowatt solar PV system. But it's true net zero in the sense that, and here are some of the things that they're using: induction cooktop, heat pump hot water heater, mini split heat pump for heating and cooling, compressor outside, typical stuff in terms of that, in terms of electrification. Then we've got a Zender ventilation system with heat recovery and the battery for the car. Cars and the battery for the car are not part of the passive house calculation, but you can end up getting essentially free car uh, uh, powering with the reduced demand that the house needs because of the passive house. So the results from this house, and this top blue line is the typical houses in the building, in the zip code. Sorry. The lighter blue line is the predicted energy use by the energy model, and the yellow line is the actual use. And so you have this pretty nice flat line. You have a pretty substantial reduce in demand of 40% of overall energy use, 38%. And what it does is, rather than having this wild swing of power, it's much more consistently tuned. And we have a 726 kilowatt hour monthly average used and 797 monthly average produced without huge gaps, which is quite nice. Other homes just over in the west, Santa Fe, New Mexico, up in Olympia, Washington. They can be any style, any shape and size. One of the interesting things is architect, and I stopped practicing architecture, ironically, back in the day, shortly after those first few projects that I did, because I got into passive house advocacy and growing the capacity in the United States. But as an architect, what really intrigued me was this idea that, what Passive House was focusing on was the architecture, was the structure, was the fabric of the building. And it really was empowering the structure of the building to drive performance. And many architects may see that as, a burden, like, gravity is a burden. But I think the way to really look at it is, getting back into the details and how before we had big central air conditioning systems, we worked with building form to provide shading and to provide more comfortable spaces while still connecting to the outside. And so we see teams really getting kind of jazzed by that, and also the builders as well, as they're just not putting together a kit of parts per se. They're putting together a whole optimized machine in a way, and what they do really is going to drive the performance of the building in a measurable way. Passive House, of course, didn't come out of nowhere. There were precursors, and we have in Scandinavia and Germany buildings and studies done in the U.S. and in Canada. Interestingly, uh, the Norwegian polar explorer ship, the Fram, had all the attributes of a passive house. Uh, Vernacular architecture, of course, and I think one way when architects and passive house architects are working on it, they may still be doing modern buildings, but to look at the vernacular architecture and what happened, in particular of China, of southern China, Swedish academic Bo Adamson was doing research on the buildings of southern China and their passive attributes, which led directly to um, the creation of the first modern passive house building, completed in 1991, with Wolfgang Feist, who we had that quote with earlier on. It's not a single family home. It's actually four flats, more like four row houses, small multifamily building with units. They did it as a physics experiment. They had custom windows, custom ventilation system. They tried to make it as low energy as they could go and kind of test the boundaries and see what was possible. The story goes that Amory Lovins came from the Rocky Mountain Institute, visited, and was super excited. Was like, "My gosh, this could be scaled. This isn't just a laboratory experiment. You need to roll this out." And from this initial experiment, the Passive House Institute was formed in 1996. They kind of formalized the protocols, the energy modeling, and have been doing. The institute is a research, building performance research laboratory institute that they've been doing research at around Passive House ever since. So one of these things hitting this low energy state we saw with the Massachusetts school example, how it really crushed that heating load. It's, you know, as well the Sunnyvale home uh, uh, is having specific targets. It's not percentage improvement. So we're going for a number, and that kind of changes everything in terms of our optimization and staying focused on it. Decoupling power from performance is kind of the idea. We expect it from our phones, from our computers. They're ever more powerful. They use less and less energy at the same time. Uh, Passive House does this for our buildings. So we have a typical leaky house with all sorts of losses below the line. Above the line is some solar gains, little internal heat gains, and then a big heating component. Our modern houses are better, but Passive House really pushes it. And when we get down that low, this quote unquote thermos state, it frees us up to not need to necessarily use traditional methods of heating or cooling. And we don't need to put the radiator under the windows. We can pull things back to the core of the building, um, and deliver comfort without that power. There are specific numbers involved. So the criteria has three new building standards. Well, three standard new building standards: the classic, plus, and premium, and then a low energy building standard. If you don't quite make the airtightness or the energy marks of the classic, there's a heating demand number, a cooling demand number with a variable allowance for humidity. There's an airtightness number, which is very famous for being super airtight. Basically, when Passive House came into the United States, everybody's like, oh my God, this is ridiculous. This is crazy, airtight. The Germans are crazy. What happened though very quickly was that the builders could hit point 0.6 ACH 50. And they could even, after they've done a couple of the buildings, they could hit point 0.4, point 0.3, point 0.2. And if you can design your building, and there are many examples of this now, where if you're in a tougher climate, um, you could design the energy model that shows your air tightness at, say, not point 0.6, which would be the standard default number for the standard, but at point 0.4. And that's going to allow you to use less insulation. It may allow you to optimize the windows in a different way. So there are all these variables and trade-offs that you are calculating iteratively through the design process. Uh, there is an energy limit, but it's based not on the source EUI carbon emissions number that we would have done traditionally, although you can calculate that in the PHPP. It's done based on this primary energy number. So it doesn't correlate directly, but you're being graded on your suitability to the future power grid. There's also a retrofit standard. So you can do a retrofit and certify to the standards, but because typically there's going to be conditions with an existing building that make it very difficult to do that, they have the retrofit standard. There are two pathways. Um, the You could do the different demand levels where they've eased them up, or you could do a component method where the different assemblies require different R and U values depending on your climate zone. You're still calculating, still goes into the energy model, but you have more of a um, slice and dice kind of approach to it that can be easier to optimize. Um, these are two fun projects in terms of retrofits to think about what's possible. On the left is classic brutalist building in New Haven, Connecticut by Marcel Breuer for American Rubber back in the day. It sat vacant for many years and has recently been reborn as Hotel Marcel and is certified Passive House retrofit. On the right is a garment factory in Sri Lanka. So hot, humid climate, factory use, and a retrofit. So a lot going on there. Predictable performance is the thing. Uh, you know, we can do energy efficient buildings, just, within the bounds of using the building code. We'll need to do better than code buildings to be really energy efficient, but you don't need to follow a specific program. You just need to get there. Um, but there's no assurance of getting there without clear guidelines. And LEED is great for a lot of things in terms of sustainability and definitely can be worth doing. Energy use at the end of the day and the benefits that arise directly out of that, um, uh, perhaps not the way that LEED is built. And so you could have a really bad performing LEED building or a great performing LEED building, but you could still have LEED certification. In a passive house, there's going to be some variability. There's occupancy, uh, uh, user differences in how they might use the building, but we're going to have a pretty narrow band of usage. That house that I did, that first house in New York, the townhouse, was actually in Brooklyn Heights. It was a pre-Civil War building, 1849, I think it was. Um, all the other neighbors had 12 to 15 tons of air conditioning. Our uh, calculations said that we needed 1.5 tons. And this is for a 5-story, 5,500 square foot home. And that's scary as heck when your client is spending a, a fair amount of money gut renovating a home. And so we knew there was some variability. We increased the size of the mechanical system from 1.5 tons to 3 tons. But we're still dropping from 12 to 15 tons to 3 tons. And you better be sure that you're going to be hitting that, or we're going to have very unhappy uh, clients. Um, and the passive house methodology is what gives us that confidence that we're going to hit the predictable performance. So super important in terms of the overall design optimization, in terms of controlling costs as well. Passive house is high quality construction. It's going to typically cost a little bit more. It doesn't have to cost a lot more. In multifamily buildings today, we see it costing 2 to 5% more, uh, pushing towards parity. This graph on the left shows the black dots are conventional buildings, cost per square foot this way, size of the building this way. The blue dots are the passive house buildings. It's a scatter shot. There's no relationship between conventional and passive house and the cost per square foot. Uh, which just tells me that there are a lot of drivers of cost in a project, and passive house does not need to be the overriding cost factor. And that if you're optimizing, you can control the costs and you can even come in very close to cost parity. Here, this is multifamily again. They actually came out with the passive house being slightly less, if you can believe it, than the conventional. This is Pennsylvania Housing Finance Agency. I'm not going to sell that passive house costs less. It is high quality, but it does show that the optimization is there and possible. What you need to really focus on is applying passive house from day one in the program and really have it there as key programmatic element. Like gravity is a key programmatic element. Um, we want to work with a certifier from day one. A certifier can cost a few extra dollars, and there is one in the East Bay, Steve Mann, is an early adopter. He's a passive house building certifier in Berkeley. Um, Work with him or another one of the certifiers. There are over 35 now working in the United States. Um, and they can really help you avoid costly mistakes and help move the project on along in a smart way. Have the team have some proper training and stick to those goals. It will actually help keep things on target. So let's dive through the methodology a little bit more detail. We'll go through this pretty quickly. Um, So the climate specific insulation levels, in your neck of the woods in California, unless you're up at the higher elevations or further north, I'm imagining it's not too difficult in terms of the insulation levels. It can be pretty modest. The idea is going to be continuous and appropriate. So it's not reacting to the environment so dramatically. I like to say that our conventional buildings are kind of like our teenagers who are wearing hoodies on cold winter days. Um, and it's just substandard. We wouldn't dress ourselves like that, and we shouldn't be dressing our buildings like that. We want a good parka that's appropriate to the weather. Um, we want that parka and insulation around the building to have as few thermal bridges as possible. We want to calculate them if we do. Even if we don't, there are pluses and minuses to it. And we're going to be looking at every intersection, the floor to the wall, the roof to the wall, where structures coming through, how the windows attached to it. It's a big difference between conventional energy modeling and passive house, where we're really nailing down all of these parts. Because what you can have is like this diagram, we have the wall and the floor, you have insulation, but then you have the masonry coming up through, stopping the insulation, and we have a masonry unit that is not insulative, and we have a thermal bridge. It's not thermal bridge free. However, if we just substitute this material for AAC block, porous concrete block, it's going to be insulative enough for it to not be a thermal bridge. It becomes thermal bridge free. It's keeping the surfaces warmer, the structure warmer, and maintaining that performance. So it doesn't need to be elaborate. It just needs to be thoughtful and intentful. Um, you know, we want thermal bridge-free construction because in a passive house, typically we're going to have better humidity conditions than we would in a conventional house. We're going to have targeted between 40 and 60% indoor air humidity. In the winter, that'll be pushing towards the 40, in the summer towards the 60% typically. And if we have thermal bridges, if we have cold surfaces and we have more humidity, then we're going to have condensation and mold problems. This is just conventional building, but so be it. So we, very much zero in on that. Typical buildings, there's so many thermal bridges, they're basically radiators to the world. We want to make sure our components are in alignment. And again, we have that good, good thermos construction. Airtight, we also now call it smoke tight over the last few years of wildfires. And we experienced it in New York actually a year and a half ago or so. Um, uh, with our skies becoming orange, and airtight construction keeps the outdoor pollution out. It also reduces drafts. It reduces moisture damages. It allows us to control the humidity inside with much less energy, allows us to control the temperature with much less energy, and make sure we have good control of that indoor air quality. Now, with the ventilation, we know we can really, with a small amount of energy, maintain a very high level of indoor air quality. So air tightness is fundamental to a whole range of aspects of performance, like a windbreaker over a fleece sweater. The windows typically are going to be triple glazed and truly thermally broken. They don't always have to be triple glazed. It's very climate dependent, but often. And we see this as part of the fire resilience as well. You can see the air tightness, um, but also the triple glazing, the simplified form in some respects, a number of aspects of passive house design, while not done so with the intention of being fire resilient, do add to the building's fire resilience, wildfire resilience. There's going to be, triply gasketed as well for air tightness. We're going to look at shading, and hopefully shading becomes an architectural element. We want to use all our space comfortably. The triple glazing is really a comfort-driven thing, and we want to get away from the typical where the glass gets too cold. We feel the asymmetric radiation losses, causes convective currents, things we have to overcome with mechanical systems. If we can get that temperature close enough to the other surfaces, we have a much more thermally calm space. And so you have the acoustic calmness, you have the thermal calmness. It is something like typically when people visit a passive house and they experience that, they're like, oh yeah, I want this. This is nice. It does not feel weird. It feels really comfortable. Hygienic ventilation with heat recovery. So hygiene, right? Good hygienic indoor conditions was a key part of that definition initially. So we're supplying fresh air 24/7 continuously to all the served spaces, the bedrooms, the living rooms, the offices, the classrooms, the assembly places, the conference rooms. And we're exhausting from the served spaces, the bathrooms, kitchens, hallways, utility rooms, and so forth, and laying it out in a way to make sure that we are going to have good ventilation no matter the conditions outside, and know that it's guaranteed. Because we're running it 24/7, we're running that air and it's 100% supply and exhaust. We're running it through a heat exchanger and we're recovering that air. Let's see. So we're also filtering the air. We're getting rid of the allergens and making it more healthy and comfortable. But as that air is going out, the fresh air is coming through counterflow heat exchange, and we can now get heat recovery over 90%. So very little energy loss with the really good units and really good comfort. They're also very quiet. It's just two fans running, very energy efficient fans. It's like having two bathroom fans running, but now you're ventilating your whole house, decentralized or centralized. So we've established the performance, then we right size the heating and cooling. We're talking about typically around a 75% reduction in sizing. Typically now it's, heat pump, it's combined heating and cooling. We can pull the distribution to the core of the building. We still want to put the conditioned air into the spaces we need it. But we can pull it to the interior walls, and it doesn't need to be in any particular spot per se. It just needs to be in that space. So it's freeing up a lot. The insulation may take away a couple inches, but the mechanical systems can give back some inches as well. Once we've added the heating and cooling, now we're talking about renewables and smart systems. You can do a smart system, you can do renewables, it's part of the standard. What we don't want are the smart systems and renewables to compensate for poor performance. We want them to enhance high performance. So we've got our optimized design. It's going all around the world. It's applicable everywhere. It's really, in many cases, although it's about climate mitigation initially and reducing carbon emissions, it's very much also about adaptation, that as the heat waves come, as the freezing polar vortexes come, the power outages come, wildfires come, that these are more resilient, safer spaces to be in. And here's a single family house in Los Angeles that was not near the fires, but a great example, very compact, quite modern looking, with solar panels, the typical kind of setup as we saw, although they did the solar shading to great effect on this building. And a quick look around at some other building types. So this is a indoor rec center. There's like 4 swimming pools in this building. So we're talking about, accommodating pretty complex occupancy groups. Fire station in Vancouver. On the left is the Dutch and Belgian embassy in Kinshasa, Congo, hot, humid climate as well. Humid climate in South Korea, an education center. Beautiful buildings. College in the Northeast on the Atlantic coast in Bar Harbor, Maine. And new schools that were just completed this past year, an elementary school and a high school in downtown Brooklyn in New York City. So a range of things, everything's possible. And I'll make the pitch that if you're interested, and we have a certified passive house designer course coming up starting on April 9th. There are a series of live online activities over the course of the course, and then there's exam review, and you take the exam in June and become a certified passive house professional. And financial incentives are available. PG&E again offers them. I think I actually have. Do I have this? This is the form from PG&E right here. And this is the one to the cohort. More information about that. But you can get the whole schedule, everything that it's about. So any questions? No questions? How much does the certification cost? So it depends on the deal that PG&E is going to provide you. If there's no incentive applied to it, it's $2,295. PG&E's incentive though is quite generous, and it could be as much as half the cost or even more. Um, so uh, uh, it could be extremely affordable. Can a 100% naturally ventilated building be certified? Well, it can't be solely based on natural ventilation. You can say that, when it's appropriate, you can ventilate 100% with natural ventilation, but you need to provide mechanical ventilation that meets the technical requirements, because there's going to be many, many, many times during the year where it's not appropriate to provide natural ventilation. The stats, one of the interesting story out of the UK, a really great firm, Archetype, was a huge believer in natural ventilation and for the schools that they were designing, and heard about Passive House for a number of reasons. We're not really sure about the whole ventilation aspect of it and looked to do some hybrid things. Um, and then they did a Passive House and they collected data. And what it showed was that the naturally ventilated schools had pretty atrocious indoor air quality. And the Passive House mechanically ventilated schools had dead on consistent, excellent air quality. Um, and they could still provide natural ventilation for the schools when it was appropriate, but they had the mechanical ventilation, so it wasn't a question. Yeah, Santa Monica near the cost. Um, uh, well, sure. So no AC, which is good. So, shading, good insulation, good cross ventilation, natural ventilation. There's no problem with that. But you do need to have mechanical. Um, how do we find out after we pay? The cost for it, I would say um, uh, um, you just do the application with PG&E and they'll get back to you and figure it out. You don't need to like be on the hook until you know how much it costs. There's a city, Mexico or New Mexico, that is ancient 100% natural ventilation. Yeah, lots of great examples of using natural ventilation in the Middle East for certain, and South America and um, lots of places. But with Passive House, we want control of it. We want predictability of it. We don't want to be at the mercy of the weather. Uh, how much does local climate play a role, for example, California Passive House versus Vermont Passive House? So you're designing for the climate, right? So you're going to require more insulation in Vermont than you would in Southern California or the Bay Area. The window, the optimization of the building is going to be slightly different. But you're dealing with all the same ingredients. It's basic building details and components that you're manipulating. So it's really about the architecture. So in the energy model, the climate data in the energy model, and you make it work with that. So about integration of fire resistant construction with Passive House. Yeah, so it's really interesting. The WUI and all of that. We've done a number of presentations on Passive House and fire resistance. If you go on our website, passivehousenetwork.org, under resources, there's a video library and there's one on fire resistance and resilience. And so we were saying there was this house that got, or I don't know if I did mention it. There was a house that got a lot of press in the Los Angeles fires. It wasn't really a passive house, but it had some passive house attributes to it that didn't burn down, but all the houses around it did burn down. One of the key things that was similar with passive house is having multiple panes of glass. In passive house's cases too. air tightness, pretty good air tightness, and pretty good simple form. And those things go a long way. Not having a vented attic space and controlling the venting on the building construction. So Passive House is not designed for fire resilience per se, but the strategies that make Passive House work also make it more fire resilient, if that makes sense. You need, the landscaping around a home or building is going to be very important as well. Interestingly, non-combustible is not as big an issue, although certainly you want Class A fire spread materials, fire resistant materials. But it's not like we need to build concrete boxes. One of the interesting things was, in Southern Europe where they've had lots of wildfires in Greece or whatnot, that's all masonry construction. Those houses all burned out from the inside. Um, uh, so that's no guarantee. One of the things that saved the house in Los Angeles was the multiple glazing, and so when the outer glass could shatter, the embers didn't have a free path in. So it's more pollution, more protected. Um, so that Yeah, so definitely, we're going to be working, and hopefully we worked with folks in Colorado after the Marshall Fire in Boulder County a few years ago, and building awareness about, energy efficient, higher performance buildings and the fire resilience aspects of that. You mentioned Passive House keeps pollution out. However, indoor air quality is much worse than outdoor. Can you explore this more detail? Thank you. Well, indoor pollution is worse if you don't have good ventilation. If you have good ventilation, it can be guaranteed to be better than the outdoor air. Um, and so, you know, unless you're in some pure spot, but like I go to the country, I live in the city. I grew up in Vermont and had horrible allergies. If I go back to Vermont, um, the pollen and other things like absolutely kill me. And while I may want to have the windows open sometimes to be able to shut it down and have good indoor air quality and not be choked by my allergies, is much better. So we can absolutely maintain really good quality. And the schools case that I mentioned earlier is part of that. That they could do that. So I was just looking at the Passive House California website, and there's designing for a fire resilience webinar on March 14th. Yes, that is Passive House Accelerator that is happening. Absolutely, check it out. Should be great. Bronwyn Barry, who is from San Francisco, will be talking about that, and Andrew Mitchler from Colorado, who is part of the Marshall Fire rebuild efforts. Should be a great program. What cohort schedule is on weekdays? Is there a weekend option? So it's basically the cohorts meet every week or two or three, depending on where you are in the schedule. And depending on what it is, it could be for an hour or 2 hours, or a couple of times it's 3 hours. They're typically on, I want to say Thursday. I don't have it in front of me anymore. But it's it's very pinpointed. It's very surgical in terms of the use of the time. Most of the time is going to be spent using on-demand materials, and that's completely at your own pace. You could do 90% of the work on the weekend. That's, totally up to you. And if you do miss a live online class, they're all recorded, so you can have access to them. And you can have access to, if you have questions, you get access to trainers and other folks who can help answer your questions. Great. Well, thank you so much. It's been a pleasure. And if you have any questions, my email is Ken, K-E-N, I'll put it in the thing, K-E-N at passivehousenetwork.org. Feel free to email me. No problem. All right. Have a great day, everybody.